which is translated into a program, which is then executed by the machine step by step, while an analog computer changes its structure according to an analog computer program, so that it will be a model for the problem you want to solve. So an analog computer does not need memory. It does not need a control unit, apart from a very, very simple control unit. It has no problems with von Neumann bottlenecks or whatever, because you get rid of the stored program concept. And that is where the future of analog computing may lie when combined with, for example, FPGA's field programmable gate arrays. Let's have a look at a very, very simple example. What are analog computers good for? Analog computers are brilliant for solving differential equations or systems of differential equations. Where do you need differential equations? Everywhere. Differential equations are the language of nature. Differential equations describe everything around you, from simple simulations of mass spring damper systems to every phenomenon you experience in nature. Everything can be described as a differential equation or a system thereof. Let's have a look at a simple differential equation. The first equation shown on this slide. We have y dot dot dot, the third derivative with respect to time of some variable y, some function y, and we have lower derivatives. And the first step is to transform such an equation to solve it for the highest derivative. So if I knew, what I don't at the moment, but if I knew what the value for y dot 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 is, I could easily derive the y dot dot and the y dot and the y. How? By integration. And integration is astonishingly simple in an analog computer. You have computing elements that implement integration. Most of you will remember integration as some kind of hard operation from mathematics from school. That's not true. Integration can be very, very simple. Collect water in a bucket. That's integration. Collect current in a capacitor. That is integration. Count bits in an accumulator. That's integration. So it's simple to build an integrator. And assuming you have an integrator, the symbol for an integrator is shown on this slide, you can derive lower derivatives from a given higher derivative. If I knew what y dot 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 is, I could derive minus y dot dot. The minus is just for technical reasons. Ignore it. And by another integration, I could derive y dot, and yet another integration would yield the plain variable y. Now I have all variables which were part of the original equation. And you see, these variables are summed with some coefficients to yield a value like 0, or if you look at the second form of the equation, to yield the value y dot dot dot. So if I take this subcircuit and introduce some feedback paths, I can yield the highest derivative, which I was looking for in the first place, by adding minus y dot dot and minus y dot and minus y to yield eventually the y dot 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 that I was looking for. And what is this? This is a program. That's a program for an analog computer. Regardless of how you implement your integrators, your summers, your coefficient potentiometers, which are represented by these circles, you can program a machine by diagrams like these, because these diagrams describe the structure of the machine, which will be an analog, a model for the problem you want to solve. That's just a very, very simple example, but I hope you got an idea how an analog computer is programmed. There's much more to it. The basic problem in programming analog computers is called scaling. A traditional electronic analog computer has a problem. It only has values between, for example, plus minus 10 volts. So you have to squeeze your variables into this area of values which can be used in the calculation. This makes solving stiff differential equations and the like very, very hard on a traditional analog computer. But using modern technologies could make this problem much easier. And we could even apply, for example, integrators based on floating point numbers, and we could get rid of the scaling problem which traditional machines have. So what we need is a collection of elements which perform basic computations. And the first idea which comes to mind is an FPGA, a field programmable gate array, isn't it? So one could employ an element which is already established in the market, very cheap. You can buy FPGA evaluation boards for a few euros, and you have the chance to get an amount of computational power that is not even paralleled by graphic processors or the like. Let us have a look at typical computing elements. What would you need to re-implement an analog computer using modern devices? First of all, how do you implement it? Don't laugh. One implementation variant is mechanical devices. This may sound silly, but at least jets like the Starfighter or the like employed mechanical analog computers, because these are rugged, nearly undestroyable, and you can implement rather complicated functions easily with gears and whatever. But that's not an alternative for today's implementations. Then you could use analog electronic implementations of typical computing elements. Analog electronics allows very high-speed operation. If you build integrators with capacitors in the range of a nanofarad or the like, you can achieve repetition rates for solving differential equations in the area of tens of kilohertz, which is next to impossible with a digital computer. The problem is analog electronics has problems with drift effects, has problems with noise, is hard to maintain, so maybe analog electronic is not the right way to go in the future, but I will show an example where someone implemented an all-integrated analog computer, but this might be too sophisticated. And the last point became feasible during the last 10 or 20 years, a digital implementation of an analog computer. These digital implementations were called traditionally DDAs, for digital differential analyzers, because an analog computer was also known as a differential analyzer. It analyzed differential equations. And the digital differential analyzer does just this, but with digital elements. Let's have a look at typical computing elements which we would need. The first is the simplest one. You need some means to introduce a coefficient into an equation. This is traditionally done with a potentiometer in analog electronics, but you could do it with a multiplier, you could do it with a shifter, whatever. You need a summer, something that computes the sum of a number of values. You need an integrator. Maybe you can just employ simple Euler integration, just summing over slices which are defined by the function you are integrating over. You need multipliers. By the way, just a historic remark, it is funny, at least for me, that multiplication is much harder to achieve with analog electronics than integration. Multiplication is really, really hard, and integration is really simple. I would never have guessed this when I was in school. You need arbitrary function generators. There are many phenomena in nature which expose functions that cannot be described analytically in an easy way. So arbitrary function generators are not that simple using analog electronics, but completely simple using digital electronics. Just implement a lookup table or whatever. You need limiters, backlash, hysteresis, just a bunch of nonlinear functions. You need comparators, for example, to compare two values. And maybe if you are implementing a flight simulator, you need a resolver to transform coordinate systems or to rotate coordinate systems. Let's have a short look how elements like these have been implemented in the past. This is not very much in the past. I think about 10 years ago, Tim Robinson implemented this particular differential analyzer from Meccano. Most of you know Meccano, and you can achieve a remarkable amount of precision with devices like these. This machine is capable of a precision of 10 to the power of -3, just by mechanical integration. You see the glass discs, these are the heart of the integrators. But that's just for historic reasons. This is the original drawing of Mr. Schwarzel, who developed one of the first operational amplifiers. And this operational amplifier is a special one because it is already connected as a summer. This device allowed for the first time to sum values by electronic means. You have several inputs, okay, modern technology. You have several inputs, in this case 3 inputs for variable inputs and 1 input for a fixed input which can be set by a potentiometer, and you have a three-stage simple operational amplifier with a feedback resistor, and the load gets a voltage that corresponds to the sum of the input voltages and their respective currents. This was in the 1940s. Since the 1940s, mankind, were able to build electronic analog computers. This is another example. This is one of the first electronic integrators, which was developed in 1941 by Helmut Hölzer for simulating the A4 or V2 vengeance weapon, the large rocket developed by the Nazis. And you don't develop such a rocket from scratch. You need some means of simulation. Controlling a rocket is a really hard task, and therefore Helmut Hölzer developed the first analog computer that was a general purpose analog computer. An interesting remark, since he was unable to build a DC coupled operational amplifier in this time due to drift effects and the like, he had to use an AC coupled operational amplifier, and he had to modulate and demodulate the voltages that were fed into his device. Very interesting. If you are ever in Berlin, the Deutsche Technikmuseum has a replica of his first analog computer, which was built by Helmut Hölzer himself. This is another example of a summer, a real summer from the George A. Philbrick Researchers Company. You have, in this case, 4 inputs for variables. I hate this laser pointer. Okay, forget the laser pointer. You have 4 inputs for variables on the left-hand side, and you have a dual output on the right-hand side. And using elements like these, you can just plug your program, your analog program, which you have developed like shown in the example above. Here's a very interesting device. In the late 1950s, early 1960s, a digital differential analyzer called TRICE was developed. And this particular machine was based on a serial design. So you could use single wires to interconnect the various computing elements, but you had the advantages of digital electronics. You had no noise, you had no drift effects, you had arbitrary precision if you needed, and so on. And this is, for example, a multiplier which was employed in TRICE. By the way, multiplication was implemented by dual integration. Okay, let's have a look at classical applications and classical analog computers. Where were analog computers used? Nobody seems to remember about analog computers, but next to nothing of our current technology which is surrounding us would be possible without the analog computing heritage. For example, in mathematics, of course, differential equations, partial differential equations, and the like were computed. Physics, chemistry are all easily understandable. Engineering, vibrations, rotating systems. If you have ever been in a Pullman vehicle, which are known for their smooth ride on a railway, these were known for their smooth ride because Pullman was the first manufacturer who established an analog computer laboratory to simulate their railway vehicles before they built them. Other companies did the same when they realized that Pullman had a real advantage. Nuclear technology, of course, you want to simulate a reactor before something goes wrong. Biology, medicine, ecosystems, metabolism research, there are some scary stories from the former German Democratic Republic about metabolism research in athletes, really scary stories. Geology, economics, market simulations. If you have ever heard of Phillips, the one with the Phillips curve, he developed analog models of markets with fluid analog computers involving water. If you are ever in London in the Science Museum, you have to see the MUNIAC, the Finanzcephalograph, which was a purely water-based analog computer, and it's a joy to watch. You see the water bubbling through pipes and filling into buckets which are weighed at whatever, solving equations, by the way. Electronics, power engineering, everything surrounding us is based on analog computing. It took many, many years before digital computers could take over. Here's an example, sorry for the bad quality, but the original image has a very bad quality. This is the so-called GPS, the general purpose simulator. Back in the 1960s, when the United States of America prepared their moon landing project, the Apollo project, you have to have some way to simulate a rocket as large as the Saturn V. Why? Because such a rocket is a mechanically very complex device. It has bending moments in all axes. It has to be steerable during flight and so on, and you have to simulate this. And this particular machine was especially built to simulate the flight of a Saturn V rocket. And it was able to simulate 50 complete flights of the first stage per second, solving all those differential equations describing a rocket more than over 100 meters in length, subject to aerodynamical forces, to bending moments and the like, 50 times a second. So you could see on your oscilloscope the solution of the functions you were looking for in real time, and you could just twist the potentiometer and introduce some error terms or change the structural stability of your rocket, whatever you like, and see immediately the effect your changes have. That's another example, in this case, one from Germany, the Deutsche Forschungs- und Versuchsanstalt für Luft- und Raumfahrttechnik, DLR. This laboratory had 3 large EAI computers, and that's a typical arrangement for simulations in the aerospace industry. You need many, many, many computing elements to simulate a 6 degree of freedom system, which an airplane or a rocket represents. You have 3 translational and 3 rotational degrees of freedom, and simulating these requires a very large amount of hardware, and that is a real disadvantage of analog computers. With stored memory digital computers, you can, in principle, tackle any problem as long as it fits into your memory. If the problem becomes harder, it just takes longer for the machine to solve it. With a traditional analog computer, you don't have a way for this trade-off. If you don't have enough computing elements, you can't solve the problem. That's a real disadvantage of the analog computing paradigm. And that's the reason why analog computers in aerospace tended to be very, very large installations. Here's another practical example performed on a machine which I have at home. The simulation of airflow around airfoil, Joukowsky airfoil. Simulating airflow around airfoil is a really hard problem. And the first step is, in this case, I need a Joukowsky profile, which is a conformal mapping of a circle into the shape of an airfoil. And that's the computer setup for the generation of the airfoil shape. And when you have the airfoil shape, you need a computer setup which computes the flow of an air particle around this shape, which is done with this particular circuit. The result looks like this. This is the completed program, and a simulation run looks like this. I can compute 16 airfoils in different positions below or above the airfoil in real time. And not only in real time, I can compute it faster than real time by pressing a simple switch like 10 times faster, which does nothing else than speed up every integrator by a factor of 10 by exchanging its integration capacitor. It's just brilliant. If that takes too long in real time, just change your time constants on the integrators, and you can really see ecosystems or airflows or whatever evolving from your mathematical description. So much about traditional electronic analog computers. We need to talk about DDAs, digital differential analyzers. The idea is exactly the same, just abandon the analog electronic part and implement all your computing elements by digital electronics. So you get rid of the drift effects, you get rid of the problem of the very limited precision. Some authors argumented that the limited precision of an analog computer was in fact an asset and not a drawback. Why? Because nature has very limited precision too. And there are some interesting papers about this topic which argue that in some cases the limited precision computation yields better results than today's modern Runge-Kutta or whatever multi-step or multi-grid methods for solving differential equations with a very high precision. But the advantage of a digital implementation is that you can just select your precision. If your calculation is not precise enough, just increase the precision by exchanging time for complexity. You have, in an analog computer, you have a maintenance horror. It's really hard to keep such a machine alive and well within its specified boundaries. You would not have this problem with a digital implementation. And an electronic analog computing is not able to be run in some multitasking or multi-user environment. One machine, one problem. No way to time share this machine. With digital implementation, you could implement a time-shared or multitasking analog computer, DDA. The first production DDA was MAD-IDA, MADIDA, developed by Northrop for simulating of airplane problems. And MAD-IDA is the rather small box on the left side with an oscilloscope on top, and the racks hold some additional function generators and the like. The basic idea of MAD-IDA was simple. Use a magnetic drum for storage of the accumulator registers for the integrators. So you have only one integrator corresponding to the arithmetic logic unit of today's computers, and this arithmetic unit was automatically time-shared between all of the integrators. If you didn't have enough integrators, you just repartitioned your drum and had more accumulators for the integrators, but it took longer for one iteration of all these integrators. So this was the first machine which employed the analog computing paradigm. There's no stored program in the memory. The program is represented by the structure of the machine, and you did not have the drawbacks of an analog electronic implementation. The problem was MAD-IDA was called MAD-IDA because it failed far too often for real productive usage. Nevertheless, it was the starting point for development which unfortunately about 10 years later died out. Digital differential analyzers were just forgotten. The next really large-scale implementation was the system TRIACE. This was developed in 1958. Packard Bell started developing TRIACE, a parallel digital differential analyzer. MAD-IDA was a sequential differential digital analyzer. You had one arithmetic logic unit, and this was cycled through all the integrators which were part of a computation. TRIACE was built in a more traditional way and had physically distinguishable integrators and summers and the like. And this is how TRIACE looked like, a very large installation. NASA in Houston had, according to some publications, 3 of these systems, and these were mainly used for orbit calculations for the moon flights and the like. And you remember the wonderful film Apollo 13. The free return trajectory is not as free as the name may imply. There's a lot of mathematics involved. And a lot of these calculations was performed on these TRIACE machines. And you see in the center of the machine the central patch field where you plug your cables in and create the structure of the computer so that it represents the problem you want to solve. So what perspectives do we have with analog computers for the future? The first thing is you don't have any overhead due to stored program control. You don't have a von Neumann bottleneck. You don't need any memory at all. Memory is just slow. Put everything into the CPU. If you have a look at the current CPU implementation and have a look at the die, what you see is only a tiny portion of the die is devoted to the actual calculations. The rest is just cache memory, control, and whatever. Nobody needs this. With an analog computing computer paradigm, you can just use every transistor you can put on a die for computation and not for storage. And the second advantage of the analog computing paradigm is you can achieve an incredible amount of parallelism. Whoever has programmed a parallel machine, when I was much younger back in university, I programmed on convex systems and on n-cubes and the like, and it was horror. It was really horror to get the most out of these machines because you had to care about, oh, I need data which is stored on another node. It takes ages to get this data through a network or the backplane to my node. Horrible. You don't have a problem with an analog computer. The data is just there where it belongs in the integrator in an accumulator register. So what could one actually implement? A very fascinating development has been done by Glenn Edward Russell Cohen. He developed an analog electronic, I'm not joking, an analog electronic analog computer on a single chip with all the disadvantages like drift effects, limited precision, but with the extreme advantage of very, very, very low power consumption. This is an actual picture of the die developed by Glenn Edward Russell Cohen, which contains about 1 million transistors, not too much in today's times, but this is very impressive. He performed some energy measurements, and he solved the stochastic differential equation. And he solved the very same equation on a traditional computer, which required about 1.2 to 40 joule of energy for the solution of this equation. A digital signal processor performed a lot better with about 0.04 to 0.4 joule for the same computation, and the very large-scale integrated analog computer he implemented only used 0.008 joule for the same computation. This chip achieves 6.4 gigaflops with only 300 milliwatts of electrical power. 6.4 gigawatts. If you have a look at Wikipedia, you can find some tables with energy per gigaflop. And as of Hume, I think, 2012, the Green 500 list rates Blue Gene Q as the most efficient supercomputer in the top 500 in terms of flops per watt, running at 2.1 gigaflops per watt. Cohen's machine performs 10 times better. And Cohen's machine was built in 2005, 8 years ago. 8 years ago, we had everything at hand to implement computation with only a tenth of the energy consumption of traditional stored memory digital computers. Unfortunately, nothing came out of this development because Mr. Cohen got a professorship for another area and had to switch his interests, which is really unfortunate. So maybe field programmable gate array implementation would be better, because who of the people in this room has the availability of the necessary equipment for manufacturing your own VLSI chip? No way, unfortunately. But an FPGA is readily available, and you only need to write some VHDL code or the like to program this device. With an FPGA, you could achieve arbitrarily high precision. You don't have drift effects. There's no need for complex interfaces between the analog part and the digital part. An analog computer alone is next to useless in today's times. You have to interface it with digital machines. If your analog computer is implemented in an FPGA, there is no complex interface. You don't have the need for a digital analog and analog digital converter, nothing. And it fits readily in our current stored program computer paradigm. There's a web page course, the CIT Cornell EDU, which focuses on the idea of using field programmable gate arrays for implementing analog computers. And this is just an example code for a field programmable gate array, which implements a mass spring dumper system and solves this mass spring dumper system in very rapid succession. So we have three alternatives. The first is a purely analog implementation, which is really cool, but I think not a real option due to the lack of manufacturing capabilities and the like, at least for hobbyist usage. One would need substantial amounts of money for going into this direction. The advantage of an analog electronic implementation would be the very, very low power consumption of these systems. The next idea would be implement a DDA on an FPGA. And the third idea would be implement the DDA on a graphic processor. Why? A typical graphic processor is a parallel vector processor, and as long as your data is very local, you can achieve high rates of computation. And the analog paradigm has all the advantages which make it easy to write code for vector processors. So maybe going through the analog paradigm and developing programs for graphic processors, graphic cards, would be a simple and cheap way to get at least some of the ideas of the analog computing paradigm transformed into today's times. So let us conclude this talk. Analog computing is far too powerful to be abandoned. Next to nobody has heard about analog computing in school or in university. I'm always shocked when I go to, for example, the University of Darmstadt and talk to the computer scientists, and nobody has ever heard about analog computing. Some people think it was a manufacturer called Analog or the like. No, it's a computing paradigm, and we should not let it become completely forgotten, because in future we need much more computing power. Just for simple things like an ego shooter, have a look at the massive amount of differential equations which must be solved in an ego shooter. If you want to, for example, see the bending moments of some grass or whatever, you have to solve a partial differential equation. Or you need flame effects or whatever. These are differential equations. You could speed this up by orders of magnitudes with an analog or a DDA coprocessor card. Simulation, for example, in eco-sciences or whatever, could gain a lot from the capability of solving differential equations much more rapidly than on traditional computers. And it is quite interesting, there is no best implementation. The implementation of Cohen, the analog electronic implementation, is very promising, but too complicated. The implementation on FPGAs seems so simple, yet next to nobody uses them. Some banks, for example, use FPGAs to speed up their calculations, their risk calculations, whatever you think about these risk calculations, but they use already FPGAs. But the strange thing is they don't use the FPGAs as DDAs to solve the differential equations, but they have written compilers which transform C programs into hardware structures. And that's just perverse, if you ask me. You could easily solve a differential equation by applying the structure of an analog computer to an FPGA. There's no need to parse a sequential C program and guess where the parallel parts are, and then derive parallel code for an VHDL description of an FPGA. It would be much more simpler to implement a DDA and just see your differential equation you want to solve as a special problem you want to solve on this machine. And maybe GPUs are a way to go for a quick and dirty implementation. We have to see this in about 4 weeks from now on. I have a hackathon weekend with a friend who is very proficient in programming GPUs, and we just want to time a GPU implementation versus an FPGA implementation and make some energy measurements just to get an impression if a GPU implemented DDA would be an alternative for the much more cost-intensive FPGA implementation. If you are interested in analog computing, where can you have a look? You can have a look at my homepage, www.analogmuseum.org. As you already guessed, I love analog computers, and I collect analog computers, and if you want to see an old, even tube-based analog computer from the 50s live and in action, just come for a visit. Most of the machines are in operational state. There are some books about this topic. The best historic source is the book from Gillois and Lauber from 1963, which can be found in quite often at ZVAB. And I myself have also written a book about this. And very interesting is the source Shileiko from 1964, who dissects digital differential analyzers. The funny thing about this book from Shileiko, or however he is pronounced, is he is a Russian. In the 1960s, somehow he got hands on American DDAs, dissected them, wrote a book about, and this book was retranslated into English and published on the American market. Really interesting how the flow of information took place in those days. Thank you very much for your interest. If you ever hear of an analog computer looking for a good home, please let me know. And happy analog computing. Any questions? I have a microphone. In fact, 2 microphones.
This is a question mostly coming out of ignorance, both things I'm going to talk about, but there seems to me to be a an overlap between what you can do with analog computing and what we're seeing with the first quantum computers, things like blue wave. Are there any problems that you think it's difficult to say because everyone thinks quantum computers are magic and will solve everything, but are there any problems that you think are uniquely suited to analog computers and that other emergent computing paradigms aren't going to be able to deal with?
It's a good question. Funnily, I got asked the very same question yesterday, especially in conjunction with the D-wave development. I'm no expert on quantum computing, but as far as I have understood, this topic is that quantum computers are great if you have NP-complete problems. Problems where you can take real advantage of the quantum superposition of your qubits. I have no idea whether you can adopt this for solving differential equations. I just don't know it. Quantum computers are definitely brilliant solution for factorization of large numbers, optimization problems and the like, but I have no clue if they are equally well suited for the solution of differential equations or systems thereof. And the quantum computer still has a fixed computer structure, like a traditional stored memory computer, and the analog computer changes its structure. So I'm not sure myself how much overlap is between quantum computing ideas and the analog paradigm. Maybe there is, maybe there is not. Sorry. Any further questions? Okay. Here you go.
Thank you. After you brought up quantum computers already, just the question.
He brought it up.
Don't be pick your magnet, please. So the question rose to my mind, how about cryptographic ideas? Is there any way to improve cryptographic protocols we have with analog computers, or break them easier, or just some cryptographic protocols?
Good question, indeed. I have to admit, I have no idea either. My diploma thesis was about cryptography, but I have no idea if you can apply an analog computing for either speeding up some cryptographic algorithms or for breaking into cryptographic protocols. I have no idea if you can apply differential equations there. I haven't done anything in cryptography for the last more than 20 years. Sorry.
I've got another one because of what you just said about an analog computer changing its structure. I'd understood that at the start, that you meant that you build the structure to solve a particular problem, but you almost seem to imply that analog computers change their structure as they compute.
They can change their structure during a computation by means, for example, of comparators and multiplexers or the like. A modern implementation could look like an FPGA with multiplexers interconnecting some macro blocks containing the integrators and various computing elements, and you would change the structure by just feeding the multiplexers with the correct bit patterns for selecting the proper input lines and routing signals to the proper output lines. A traditional analog computer really changes its structure while I, as a programmer, plug in all the plugs. But a modern implementation has, of course, a fixed design, but uses multiplexers to change the interconnection of the various computing elements.
So would a neural net, would it come under your definition of an analog computer because it is a connection-oriented structure that you wire?
Take structure in the sense of interconnection scheme between the computing elements.
But that's true of a neural net. It is about the interconnection between.
Yeah, a neural net has many similarities with an analog computer, but you can't reprogram it as easily. Okay, any further questions? If not, thank you very, very much for your interest and have a nice Sunday.